so we're discussing geology today. It's the very basics of it. Remember, geology is a field unto itself. Basics of rocks. And it's a critically important part of geography. So you can spend years studying geology, the different subtopics and different fields in it. But basic definition: scientific study of rocks and minerals. Geology. Now, geology is part of the slow process that is shaping the topography of the Earth. Geological processes can range from the thousands into the millions of years, even beyond that. Now, the two types of forces shaping the Earth. These have to do with landforms. One, forces that push, move, and raise the surface. Gentle slopes or huge mountains. Second, forces that erode and wash away the surface. It builds up, it's brought down. Process of erosion and gravity. For example, huge continental plates pushing together, those will cause land forces to rise over time, building mountains. The Himalayas, the border between China and India and Nepal, those are two continental plates shifting together, pushing up, raising the land surface, creating huge mountains, largest of which is Mount Everest. And of course, forces that erode and wash away the surface. One of the best examples of that, the Grand Canyon. That is a force of erosion over millions of years. That water cut the Colorado River, cutting away through the rock in across Arizona, creating the beautiful canyon we have today. Essentially, what built up can be brought down. And these are the same force could be used on any of the rocky worlds of the solar system. It's not just Earth. The same process or force on Mars. Mars actually has plate tectonics like Earth. In fact, it's home of the largest mountain in the world. Olympus Mons is 15 miles high because the plates moving into each other just keep pressing and pushing up this huge volcano. We see it on Venus, on Mercury. Similar processes on the moon. Because we may not realize, may not stop to think about it though, but the Earth we're standing on, it is in motion. It is changing. Very, very slowly, but it is. Now the rocks in the crust of the Earth, that is the uppermost layer of the Earth, they vary according to mineral content. Now mineral is a particular chemical combination that has hardness, density, and a defined crystalline structure. It's a lot of geology. It is chemistry. How do certain elements combine to form certain minerals? And plus, how do these react with other elements and chemicals around them? Particularly, how do they react to water over millions of years? But each can be defined in terms of hardness, density, and crystalline structure. A couple of common minerals include quartz, simple quartz crystals, feldspar, silicate, diamonds. Diamonds, that's just basically carbon that's hardened into a crystalline shape. But those are what minerals are. Hardness and color can vary according to mineral content. Like say if it's mixed in with something or close to some other sample or ore, it can affect that chemical combination. In effect, rocks and minerals can rust. Minerals can rust too because exposure to other chemicals. Copper, for example, over time, exposed to the elements, it'll turn green. Rust, iron will turn red. Oxidation. Again, exposure to other elements causing a chemical change and causing a change in color and hardness. Now, some resist decomposition. Others are very easily broken down. For example, diamonds, very hard to break those down. That's the hardest natural substance in the world. But others, like say talc or limestone, it can be broken down comparatively easily. It takes a long time sometimes, but it can be broken down. So you got to understand what geology all comes down to. You have pressure, time, and composition. And if you understand those forces at work in a particular area, you understand geology. Pressure, time, composition. What kind of pressures are it under, or how long, and what's there. Now, there are three main rock types. I'll get to those here. First, igneous rock. Igneous rock. This is formed by the cooling, solidification of molten rock. Because beneath our feet, several miles beneath it, all the rock has turned to liquid, magma. But when it comes up through volcanoes, it spreads out, it cools, it hardens into rock. That is igneous rock. Terms here, magma is underground liquid molten rock. understand what temperatures it takes to melt a rock, again, depends on its composition. Again, back to basic chemistry. Lava is above ground molten rock. Now, lots of different types of igneous rock, again, based on composition. May be familiar with sometimes igneous rock is kind of light and porous, has a little kind of tiny little holes in it. That is one time it's popular with gardening decorations, but that is a type of igneous rock. And so the little holes in it comes from air bubbles escaping as it cooled. But there are also types of igneous rocks that are much harder and much denser. That's just one example. And you got intrusive igneous rocks and extrusive igneous rocks. Intrusive igneous rocks are igneous rocks that form underground. Again, not a constant temperature under the surface. There are certain pockets that are cooler than others, allowing rocks to magma to solidify. Extrusive igneous rocks are, of course, rocks that are formed above ground. Like your decorative little lava rocks you use in your garden, like we talked about. Those are extrusive igneous rocks. And again, the composition of molten rock and its rate of cooling determine the type of mineral it forms. Crystallization, that is a chemical process, and that depends on a bunch of different factors. Again, pressure, time, composition. Large quartz crystals form underground and combine with other minerals to create granite. Very famous type of igneous rock. Very solid, often used in construction. But it is formed by quartz crystals combining with other minerals. And large part of the ocean is the ocean basin is formed from extrusive igneous rocks. It's called basalt. Again, that's not all extrusive rock on the ocean floor. That's just one particular type of it. This came intrusive type. Granite is intrusive, basalt, it's an extrusive, but not the only types. There are hundreds of different rock types in the world because of all the different chemicals and all the different processes at work forming the earth above and below ground. That's the first rock type. Second rock type, sedimentary. And just as the name suggests, formed from sediment. Like say, combines particles of gravel, composite particles of sand, gravel, silt, clay, eroded from existing rocks. silt, clay, all eroded from existing rocks. Sandstone is a very famous form of a sedimentary rock. Basically, it's a big old hunk of sand hardened into a rock. Like I say, you may find a lot of conglomerate types that are basically sedimentary. Basically, one rock with several rocks, different kinds of rocks in it. That's sedimentary rock. Sandstone coming from sand, of course, and siltstone coming from clay and shale. And harder substances, but are hardened into rocks. But they can be, with erosion of time, they can be hardened into stone, siltstone. Now, sedentary rocks typically evolve underwater, and is in horizontal beds called the strata. Strata, that is underwater horizontal beds. And that's where sedimentary rocks are. If particles are large and roundish, that's where you get your conglomerate kind of rocks. It can also be formed from debris from the original materials. Limestone is an example of a sedimentary rock. And very pretty rock, also used in construction. I say limestone is formed from shallow seas. Say formed in shallow seas. Shallow seas. Okay. And coal. It's a mineral, it's a rock. It is formed from decomposing vegetation. Sometimes in certain times you got a big chunk of coal, you can actually see the imprint of a plant leaf in it. Sometimes not very often. But it's from decomposing vegetables or vegetation. It's hardened into rock over time. Now, the thing about forming coal is it takes millions of years to form this. From millions of years of chemical reactions and pressure to create it. So, the Earth is forming it all the time, just not very quickly. Not quick enough to be replaceable very easily. So it can't be considered a renewable resource. Because, yes, while the Earth's processes to renew it do exist and are taking place now, it's just not fast enough. Like I said, no one can wait 2 million years, 2 or 3 million years for the next coal shipment. And many other issues with it. Now, a large part of the continental shelves contain sedimentary rocks. Now, sedimentary rocks, igneous rocks, again, this is where geography comes into this. where are these located? What types are located where? That's another issue of geography, is finding out where do we find these different types of rocks? Where do we find these different kinds of minerals? Where are they distributed? What is the relationship between these different regions where they're at? If there is one at all. And so by understanding geology, it also helps humans plan ahead, where we can build certain things, where we can build certain community kind of buildings, what type of economy an area is going to have. For example, geologists are routinely employed by oil companies to find oil and natural gas reserves because they can spot all the markers in the rocks. And there you know where to drill and where not to drill. Here's say a limestone or granite quarry, where you can set that up and how you can ship those products to market to be used as materials for construction. Or even what type of rocks are in the subsurface can determine what kind of buildings can be built. Using modern construction techniques, you can't build a huge tall skyscraper on a soft, sandy foundation because the building just wouldn't support the weight. But if you've got something like granite or limestone or something like that underneath it, yeah, you can build a tall building because they can anchor it into the rock subsurface. The third type of rock, we've got igneous, we've got sedimentary, we've got metamorphic. Metamorphic. It's formed from igneous and sedimentary rocks by heat, pressure, or chemical reaction. So yeah, even when a rock is formed, it's not done yet. Still, a lot of things can happen to it. That's where metamorphic rocks come in. Igneous sedimentary rocks by heat, pressure, chemical reaction. Pressure, time, and composition. Now you may have heard things like, say, natural diamond, artificial diamonds. Yes, there are diamonds that can be created in the lab. All the process mimic the natural processes and speed them up many more times faster than the natural processes can form them. But otherwise, a lot of these all these processes forming rocks, be like metamorphic rock or sedimentary rock, we're talking thousands or millions of years. Say coal is not formed from just being under that pressure for a few days or a few weeks. It's millions of years, very, very long time. And that's what we have to understand what we're talking about with geology is we're talking about deep time, beyond our lifetime, beyond all of humanity's existence. Say hundreds of thousands, millions of years. And there are some rocks found on the surface that are a couple billion years old. A couple of them found in Australia. You go to the moon, those rocks are billions of years old from the moon's formation. And all these processes are still in operation today. Very, very slowly. Take multiple thousands of lifetimes for us to even notice any kind of difference. But these processes are at work. Igneous, by cooling solidification on rock. Sedimentary, eroded from existing rocks formed together, and metamorphic, formed from igneous and sedimentary rocks by heat and pressure chemical reaction. For example, shale. It can form siltstone, but shale, under a slightly different set of circumstances, under pressure, can create slate. Slate is traditionally used in blackboards, chalkboards. It's a much more brittle kind of rock than, say, granite or limestone, but it's very effective. It can be smoothed over, and with chalk you can write on it, and erase it, and rewrite on it over and over and over again. So slate can be very, very useful. In fact, schools in the 1800s, kids didn't use pieces of paper so much as they used slate writing tablets to finish all their work. Limestone, under certain circumstances, can be hardened into marble. Today it's often used in decorative features of buildings, countertops and so forth. Like I said, marble shining up, looks real nice, real pretty. But marble is another form of metamorphic rock. Now, understand, formation is a continuous process. The process, the Earth doesn't start forming these things and stop. There's still work today. We have volcanoes around the world that are still erupting. That is part of these geologic processes at work. Spitting up magma, and the lava solidifies into brand new igneous rock. Erosion is a process that's happening, continuing all the time. You may not see it very quickly, especially when it comes to eroding rock, but it does happen. It is happening right now. And all those processes, metamorphic rock, happening as well. Some is out in the open, some is deep within the surface, but these processes are at work. And all coming down to what is there and what's happening there and for how long. But again, understand geologic time. A very, very deep time. The Earth's age is 4.6 billion years old. It's not a stutter, it's not a typo. That is a real number, 4.6 billion years. See, the Earth is ancient in the extreme. These aren't numbers scientists picked at random. This has been done through decades and generations of study, thousands of studies that pointed to and all confirmed 4.6 billion years. Using a variety of processes, including radioactive dating techniques, looking at engineering, looking at chemistry, radioactive decay. It's all coming down to the same number, 4.6 billion years. Because it comes down to look at the evidence. Always look at the evidence. What's around you? What's that evidence saying? Remember, sometimes you have to look at, you just have to look at the data you have and have the humility to understand it. Your initial assumption may be wrong. And through the scientific process of communicating results, scientists look at the results from their experiments, their studies, and they talk about them with other scientists. Peer review. And they all come back the same number, 4.6 billion years. Look at the data. Look where it's taking you. All pointing to 4.6 billion years. Now, of course, this is an extremely long period of time. So it's kind of time period we can't really imagine. Yeah, we can conceive of it barely, but it's kind of hard to put it in any kind of a detail here. Let's put this in some perspective. Translate the distance to time to distance. Say 1 year equals 1 inch. 4.6 billion inches. That is equal to 72,601 miles. That's roughly a third of the way to the moon. That's an average distance. 4.6 billion inches, 72,000 miles, about a third of the way to the moon. Or put it another way, go to 1 year is 1 inch, say just a million years. 1 million inches, that's just 15 miles. That's the difference between billion and million. 15 miles. I'm trying to think while you're right. 15 miles. 15 miles, that is roughly the distance between El Dorado and Junction City, right there in the Louisiana state line from here. Another way. Yardstick. This is 1 inch here, 1 inch, 1 inch. That's what an inch is. Most of you college students, 18. Put your life in terms of distance. This is how far we've gone. Middle age, 36. Get two of these together, you get the span of a human lifetime. But wouldn't even cover this whiteboard. So these are not processes you're going to see happening in your lifetime. You might see the beginnings of them. You might see the beginnings of molten rock form. You might see the beginnings of erosion taking place. But the ultimate product, what you see, continental drift, mountains forming, mountains eroded away, you're just not going to see that in your lifetime. Say 72 inches in one lifetime versus 1 million inches, 15 miles. That's still not even barely even a measurable fraction of the Earth's lifespan of 4.6 billion, which would be a third of the way to the moon. The Earth isn't done yet. Next, these dramatic processes of uplift and erosion create the current topography of the Earth. Where the hills are, where the mountains are, where the rocks and minerals are, and all the surface soil and trees and plant life, animal life on top of all of it. Process in work still today. Okay, questions? So we'll leave it at that. Next I'll continue on chapter 3 in the book, continue talking about the landforms and talk about plate tectonics and earthquakes and all that.